All right, good morning, everybody. Let's go ahead and get ourselves warmed up. Same old things we've been doing. We're going to solve some exponential equations. And then today we're going to move on to the next section. It's not that complicated. It's just introducing a new number, a very, very special number, e. So we definitely want to be exposed to that. Don't freak out when you see a new number like pi or anything else like that. It's just a number. And if you remember it's a number, and you can do the same thing with it. You can always do with numbers, then you'll be just fine. All right, so let's solve the following equations and inequalities. Number one. Write it down. We got ourselves a fraction in the first one. You have a 1/4, and that is raised to the negative x plus 6. And apparently that equals 8 to the x plus 1. Well, the first thing you should see is what? That base is not more than 1, right? That's not what we want. So the first thing we're going to do is flip this thing. So we're going to flip this fraction. And when you flip a 4th, it just becomes 4/1 or 4. So we have a 4 there. But whenever you flip it, what do you got to do with your exponent? You got to make it negative, right? So if it was negative x plus 6, I make all those negative, it'll be positive x minus 6 right there. So that's a good start. At least now all the bases are more than 1. However, they're not the same yet. And I don't think 4 raised to any power that's pretty is 8. So we're going to have to go down deeper. Do you know numbers that go into 4 and 8? 2 do, yeah. In fact, you can write 4 as 2 squared. And 8 is 2 to a power also. It is 2 to the 3rd. That's a common one. Good to know that one, 2 to the 3rd. All right, now they do have the same bases. However, their powers raised to powers. So you bust out your rule about powers raised to powers. You multiply your exponents. So right here, 2 times all of x minus 6 would be 2x minus 12 in that case. The other one, same thing. 3 times all of x plus 1 would be 3x plus 3. And now you got your bases to be exactly the same, just one exponent, not exponents and exponents, not a bunch of weird stuff. So if the bases are precisely the same, you can kind of just ignore them. And we're left with the equation that 2x minus 12 is equal to 3x plus 3. And then to finish the thing up, I think it'd be pretty easy to move the 2x over and then just have an x, and that's kind of what I'm after anyway. So if you subtract 2x from both sides, just an x over here. You have to move the 3 over though, so if you subtract 3, you'd get negative 15. So that's my solution for number 1. X equals negative 15. So there we go. Any questions over that? All right, let's try another one. Number 2. It's an inequality with a couple of fractions. Ooh, that's weird. So number 2 starts off as a 2/3. Now that's more than 1, less than 1. What's 2/3? I think it's less than 1. You're right. So right off the bat, that's a problem. And we have a 9/4. This is kind of strange. To the 3x minus 4. Well, like we already said, this is less than 1. So without even any more thought, we're going to flip this guy and negate the exponent. So we'll call that 3/2, 2/3 flipped. And not raised to the x plus 2, but the negative x minus 2 right there. That's step 1. Huh. And you're left with this thing. Well, how do you do this thing? Why do you think 9/4 and 3/2? Well, anybody got any guesses why they picked these numbers? 9/4. Well, how does 9 relate to 3? It's 3 squared. Would you agree? Oh, how's 4 relate to 2? It's 2 squared. So this thing squared, 3/2 squared, is 9/4. Is that believable? Okay. So what I'm going to do is, I'm not going to change the 3/2. Usually you change the bigger one all the time. Let's call the 9/4 3/2 squared. Why not? 9/4 is 3/2 times 3/2. So I can write the 9/4 in terms of 3/2. That was a tricky one. But it did kind of work out. Over on the right, we have a power raised to a power still, though. So we're going to have to multiply these exponents. So on the left, doing nothing. And on the right, If you take this exponent of 2 times all of 3x minus 4, you get 6x minus 8. So we found a way. We found a way. They have the exact same base now, 3 halves. So once we've accomplished that mission, I don't care if it's a fraction or something weird or pretty or whatever, if they're the same bases, we can just drop them and look at the exponents alone. So in this one, we have negative x minus 2 less than 6x minus 8. Yeah. And now we have no more exponentials. We're out of the woods on that. We just got a simple little linear thing to solve. And I like my x is positive, so I'm going to move this over here, make it 7x. And while I'm at it, I'm going to add this 8 over. If you add 8 to both sides, this would be a 6. And I'm going to divide by 7. I don't need to flip it because 7's positive, but always think about that. And it's a weird, awkward answer, but okay. It is what it is. I don't think we made a mistake. So we're looking for the 6/7 is less than x. In other words, x is more than 6/7. So wherever 6/7 is on the number line, more than it would be that way to infinity. So 6/7 to infinity, parentheses on them both. That's parentheses because it can't actually equal 6/7. It can get close, but it can't actually equal it. Questions on that? Kind of tricky with the 9/4 thing, but just keep thinking about it. There is some way, somehow, the bases are related in this entire section. So enjoy those, because eventually there will be ones where the bases cannot be the same. We have to use some other stuff. All right, now number 3 looks long. It's not that bad. Starts off as 2 to the x plus 1 times 4 to the x plus 2 times 8 to the x plus 3. And apparently this whole thing is equal to 32 to the negative x plus 5. Oh my gosh, there's so many exponentials. What do? We got to break them all down into the same base. But I think I gave you some obvious numbers here. 2, 4, 8, 32. They are all on the same row in your thing. It's all related to what? Anybody know what number these are all related to? 2s, that's right. So we're going to break them all down to 2s. Well, that's already a 2. I don't need to do anything with that. 4, well, that's 2 squared, right? So I'll replace the 4 with 2 squared. 8, what's that? 2 to what power is 8? That's right, very good. 2 to the 3rd. And over here, oh, 32. Anybody know that one? 2 to something is 32. Close. 5 is 5, yeah. I expect you guys have those memorized. It's a little too high up the chain. You should know 2 squared. You should know 2 cubed. I don't know about 2 to the 5th. That's getting a little out there. Great. All right. Well, just like anything else, we have powers raised to powers. We should simplify those. So let's just recopy things. First one's no change. The second one, well, I had a power of 2 raised to an x plus 2 power. So I'm going to multiply those together. And that would leave me with a 2x plus 4. Similarly, for the cube one, 3 times x plus 3 is 3x plus 9. And then same deal on the right. Power to a power, you multiply your exponents. 5 times all of negative x minus 5 is negative 5x plus 25. So we got all this. It's still not an exponential equaling another exponential. That's what we're after. Just one thing on the left and one thing on the right. How in the world do we put all these together? Just the same way we would do with x's. If I said x squared times x to the 3rd, you'd say x to the 5th, right? You just add your exponents, right? This is no different. If their bases are the same and you're multiplying things, you just add your exponents all up. We could probably do it in our mind all in one shot. Let's see how much is total in the exponents. X's, there's 1x plus 2x plus 3x. That's a grand total of 6x. There's some numbers too. There's a 1, a 4, and a 9. If you add all those up, that adds up to 14. So we can put all those exponentials into a single one on the left, normal little exponent properties. And we finally got it down to just an exponential equals an exponential with the same base. So at this stage, we can just drop the bases. They're gone. And now I'm just going to look at the exponents. 6x plus 14 is negative 5x plus 24. If you add the 5x over to make this side positive, you'd have 11x's. You're putting the x's on the left, you probably want to put all the numbers on the right, so we'll subtract this 14, and 25 minus 14 is, guess what? 11. So if you divide by 11, you get a nice clean answer this time. Apparently, x equals 1. So that worked out just fine. Any questions over any of that? All right, let's get to it then. So today, your LGs, next section, shouldn't be too bad. Analyze expressions and functions involving a very special number e. There's a few constants that come up in math along the way, pi, e, and they're fundamental to mathematics. Oh, that's probably fine. Phil, that's good. That's great. Thank you, James. Appreciate it. I'll take it from there. Nah, don't worry about it. Thanks for doing that at all. You did great. Proud of you. Are they commies?
No, whenever they drink it, it's like stuff that comes from a can.
Oh. All right. Well, new stuff comes new homework. So here it is. 7.2 is due today, of course. The new one, 7.3. Normal stuff. Got a couple days on that. You'll have time tomorrow to work on it. Probably have some time at the end of class, too, to work on it today. It's not too strenuous. Most of the work will be trying to justify why this number e is even a special thing.
It's the best number.
I think it's the best number.
You think correctly. Yes, it is.
I like natural log 2 also.
Natural log 2 is interesting.
I don't know why, but
I need to
it just
memorize
pops out at me.
I need to memorize natural log 2. Part of it.
Good. Comes up a lot. All right, notes. Here we go. This is section 7.3. It's titled Special Exponential Functions. Let's see what's so special about that. All right, here is the definition of e. Take a minute and copy it down. It's all fancied up with some limit stuff, and I'll try to justify why this might be useful. You really won't understand why e is useful till you get a little higher up. But for right now, at least with the finances, that stuff we talked about in the previous lesson, the compound interest and things like that, we can talk about that a little bit more in depth, and that can explain maybe why e would be a useful thing in the real world. It's kind of like pi, you know, the first time you see pi, you freak out, you're like, what is this symbol? And it just stands for some random digits, 3.14159 that goes on forever. And whenever you think of pi, you should think of, okay, circles. Well, whenever you think of e's, you should think of lots of things, but probably exponentials. And it's just a number too. Okay, so don't put it on a pedestal. It's nothing special. It's 2.718281826. It goes on forever. It's irrational, just like pi. Goes on forever, has no pattern in it. And it's just a number, okay? It's just a number. So when you start seeing a bunch of e's floating around, I want you freaking out. It's just like a 4 or a 5. It's just like any other number. It just happens to be very, very, very special in mathematics. All right, everybody knows about 2.71? Okay, put that in your mind, okay? Just like pi. Somebody says pi, 3.14, you should have a general feeling for what that is, right? E, okay, 2.71, that's kind of what that is. Now, why might that be useful? Well, let's go back to finance for a second, because last time we did talk about this equation right here. This was for compounding interest. Remember that thing where we did that? You invest some money and stuff like that. Well, let's play with some numbers, okay? Let's keep it really, really simple. Let's say somebody put $1 in, okay, very boring, and their interest rate was 100%. What's 100% as a decimal? It's just 1, right? I'm trying to make everything 1 that's not important here. And I'll keep the n, actually. And I'll just say we did this for 1 year or something like this. Naturally, from money, we kind of get this. Now, I want you to get your calculators out. Let's play with this for just a second. Let's try to justify where this e thing comes from. Let's say you did this 1 time a year. I want you to plug 1 into this equation. Type in your calculator and spit out a number for me. So type in 1 for n and see what we get. This will be a very boring number here. It is 2. Yeah, it's very, very dull right there. You just get 2 out. Now remember what that means. That means what this n means is how many times a year it happens. You remember that stuff? So if n is 1, this just happens once a year. Now, what if they break it up into, say, every month? Then n would be 12, correct? That's what that means. Okay, I want you to do the exact same thing and plug in 12 for n. So now I've taken this interest rate and I break it down to just once a month. What happens if I do it for once a month for a year? 2.6 what? 1, okay, sounds good. Well, what if I do it for, let's go crazy. Let's do it every day. Every day we're going to do this. Plug in 365 and see what kind of weird decimal you get out. 2.71-ish. Well, let's go crazy. Let's say somebody was doing this and broke it up into 1,000,000 parts. Plug in 1,000,000 into this thing. Let's see what happens when you plug it in 1,000,000. So they're going to break this year up into 1,000,000 pieces, very small amount of time. 2.71 something again? Seems to be leveling off, do you agree? No matter how big n gets, it seems to be approaching some kind of weird number. And guess what that number is? It's e, right, exactly. Now, what's this mean if you're just doing more and more times? Well, you're basically doing it all the time, would you agree? If you split a year into 1,000,000 pieces, that's not a very long time, is it? What if you split a year into not 1,000,000, but 1,000,000,000,000 pieces? Well, we don't have to do it. I mean, go ahead if you want, but guess what it's going to be? It's going to be about 2.71-ish again. Boy, if I split a year into 1,000,000,000,000 pieces, that's not very long, is it? Like it's probably like a year, like a minute each. Would you kind of agree? Basically, the higher up you go with n, what's happening? You're doing this more and more often, right? It's almost happening all the time as n gets bigger and bigger and bigger. So that's what n is. That's what e is. As n gets bigger and bigger and bigger, that's what that limit thing means, right? Limit means as n gets bigger and bigger and bigger, what happens to this thing? It turns into this. And that leads you to this equation right here. This is the same idea as before. If you're investing some money, as compounding, this is just how much money you'll get out. Letters mean the same thing as it did last lesson. A is the amount you get out in the end. P is your principal, how much you invested, same exact definitions. R is your interest rate as a decimal. T is your time in years. But when this happens basically all the time, continuously, it's called continuously compounding interest. Okay, so this, if they say the buzzword compounded continuously, well, you don't go to this equation anymore. You go to that new one on the board right there. And it says A equals P e to the RT. Remember, E is just a number, right? Okay, so don't freak out about it. Oh, I bet we should probably at least stop and talk about where the E button is on your calculator. Is that probably a good idea? Probably want to know where that is. All right, let me show you. No problem. If you go to your home screen, normal stuff, down here on the very left, there is this button that says log. That's what we're going to study next unit. But in blue, well, yeah, there's also this one underneath of it that says ln. We're going to talk about that next unit too. That stands for natural log. But if you look above it in blue, what's it say? An E thing, right? And how do you get to any of your blue stuff? You do second first, right? So you do second, and then that ln button right there, and that's the number E. In fact, if you just do E to the first, well, anything to the first is itself, right? And you hit enter, there's the value of E. It's about 2.718281828. It doesn't go on like that forever. There's some 2s and 6s after that, but something like that. So let's make up a problem real quick and see if we can see how much money someone would have if they were compounding continuously. All right, I'm going to make up a problem for you on the fly. Let's see what we can do. Here's your example. Example. Billy Bob invests $700 into an account that is earning interest at a rate of 4% annually. He keeps it in there for 10 years. And the bank account is not compounded monthly. It's not compounded daily. It's compounded continuously, which means we're using our new equation, okay? When they say compounded continuously, that's what this one is right here. But just like the last one when we did it, the last lesson, it was really easy. Just plug the numbers in, right? Same thing here. It's not going to be any different. We're just going to replace the numbers. So the amount they're going to have after 10 years is equal to the principal. That's how much you invested, correct? Which is 700 times E. Now that's just a number, okay? You always write the letter E, just like for pi, you always write the pi symbol. Raised to the R, that still is a decimal, 4%. What's 4% as a decimal? 0.04, yeah, 0.04. And then times your time, which is 10. See if you can type that in your calculator. Same thing, type in 700, e to the whatever, second, that ln button down there again, 0.04 times 10. Everybody got set up looking like this? Did you get this number? Okay, so that's how much they'd have after 10 years of compounding at that particular interest rate. And you write it down and you round it to the nearest cent like you would any other thing. So they have $1,044.27. I'm going to round down because the world never gives you that fraction of a penny. If you wrote 28, I wouldn't be mad at you or anything like that. That's all I really want to say about the money thing. Okay, are we okay that there's one more equation? And it has got an E in it, so don't freak out when you see the number E. It's just a number, and you know where that number is on your calculator right there. Okay, what other things are they going to make you do besides this kind of stuff? Well, they're going to make you make sure that you know the basics. So let's double check that you know the basics. It's the same things you've always done. It's just got a different number, okay? So don't freak out just because it says E instead of 7 or something like that. Let's write these down. A, e to the 7th times e to the negative 2nd. If those e's were x's, you'd know exactly what to do, wouldn't you? If I said x to the 7th times x to the negative 2nd, what would you tell me the answer is? X to the what? Yeah, exactly. Well, why is this any different for number 1? If they say e to the 7th times e to the negative 2nd, I wonder what that is. It's e to the 5th. Yeah, it's the same exact concept. Just because they're using a funky letter and a funky number doesn't mean the rules are any different. That's the point of that one. Part B, it's got a weird thing. Negative 3 e to the 2x. Well, that's weird looking. And that's raised to the 4th power. How the heck are we going to do this? There's lots of ways to do it. Number 1, you could just remember what raising something to the 4th power means. It means to multiply by itself how many times? 4 times. You could do that. Or better yet, if you have something raised to a power and you have 2 things, I see 2 things. I see a negative 3 and an exponential. Do you kind of see 2 things there? Well, they're multiplied together, correct? That is one time you can actually take the power and do them to them separately right there. So I can call this negative 3 to the 4th. I can do it separately. But I can also do e to the 2x to the 4th right there. That's an old algebra property. You got 2 things multiplied together to a power, you can do them separately. So that's nothing new right there. Well, let's simplify what we can. How about this one right here? What's a negative raised to an even power? We should know that. Negative raised to an even power. Positive, yeah, it is positive. What's 3 to the 4th? Well, that's on my table somewhere. I can look that up. It's 81. So the negative 3 to the 4th, and you can just type that in your calculator too if you want to, right? Parentheses, negative 3 to the 4th into 81. Now this one, what can we do with this, guys? Isn't this a power? Isn't it raised to another power? And what do we do with those? Multiply them, exactly. So this would be e to the 8x right there. And that's what the simplified version of that particular problem would look like. See? Same kind of things. These are old middle school exponent rule kind of things. Can you simplify fractions? Do you know what to do with exponents when you divide, that kind of thing? Well, I see two parts of this. I see a 42 over 14, okay? Can you reduce that? Is there anything that goes into 42 and 14? 7. 7's good. 7's big, right? Biggest one's great. So if you divide them both by 7, what do you get on the top? You get a 6, right? And what do you get on the bottom when you divide by 7? 2. Could we have done a little better, it looks like? Can we reduce 6 over 2? Yeah. Okay, so we'll have to do that again, but we'll do that next step. What about these e's? What do you do with your exponents when you divide things? Do you know? That's right, you subtract them. What's 7 minus 5? 2. So I have basically this part, and then there's an e to the 2 also hanging out. But of course, like we said, 6 divided by 2 is 3. So this is just 3e squared. So you're not doing anything you haven't done before. You're just doing it with a different number, e. Okay, you've done it with x's, you've done it with 7s, you've done it with 9s. Now you're doing it with e's, and that's essentially all there is to it. Let's see if you can do it. Let's try a few. Ooh. Try this one out on the left. You might be able to just do that in your head. What power is that last e secretly raised to? 1, right. So what are you doing with your exponents? I heard it. Everybody got confirmation? E to the 8th. Yeah, you're just adding up your exponents. Exactly. 4 plus 3 plus 1 is just 8. I love it. Oh, what about the middle one? Try that out. If things are multiplied together, you can do the exponent to them separately. $1,296. Ooh. E to the 8th. I buy that. That's practical. You guys, did you get the same thing? Okay. Yeah. 1,296. That's, I assume, 6 to the 4th. And then the e squared to the 4th. Yes, you multiplied your exponents. Outstanding. That's e to the 8th, and then you're all done with it. Good job on that. Very last one. Don't let fractions scare you. Just simplify the numbers. Can you reduce 60 over 12? I don't know. What do you do with your exponents? Yep, I'm agreeing with that. 60 divided by 12 is 5, right? And then you subtracted your exponents on the top, from the top and the bottom, I assume? Very good. And then, of course, yes, 6 minus 2 would in fact be 4. So very good. You guys got the handle of the basics. Don't let the e scare you. That's the main theme for the day. Don't let the e scare you. Okay, of course, there's graphs too with exponentials. Should you freak out with these? No, it's the same thing we've been studying. Okay. Now, e. What's the value of e? About 2.71-ish or something like that. Is that more than 1? Yep. So what's the graph of an exponential with a base of e look like? Well, the ones with more than 1 increase, right? This is no different. So if they throw a base of e, they ask you to graph it. Don't freak out. Just do what you would normally do. And let's practice this one right here. Consider this function -2. G of x is -2. We'll copy down the equation. E, I'm not going to freak out, to the x minus 3 plus 2. As much of a pain in the butt it is to figure out what a graph of an exponential is with any base, it's going to be the same pain here. No harder, no easier. Well, in my mind's eye, I'm thinking, since e is more than 1, this would kind of be what the graph looks like, right? By default. This is kind of what e to the x would look like. It's a very important graph, e to the x, like 2 to the x or 3 to the x. Well, let's see what things do to it. What happens when you multiply by a -2? What's the negative do? Flips it, right? What's the 2 do? It stretches it by 2, right? So I need to flip it. What's the x minus 3 do? It shifts it to the right. 3, correct. And then what's the plus 2 do? It just moves it up 2. Well, let's start with the moving up 2 thing. Normally, these all level off at 0, correct? If in the end I'm shifting things up 2, I guess this graph will be up at 2. So there will be a horizontal asymptote at y equals 2. We're not doing anything we haven't done before. We said it got flipped, so it's not going to open up. It's going to open more kind of downish. Something like this. Good enough. That's a rough sketch of it. If you want to know a specific point, let's see. Where does it cross? Where's the y-intercept? They always ask that. Where's the y-intercept? Kind of hard to spot with this thing. It's got ugly numbers and things like that. But nonetheless, always remember, how do you find a y-intercept? What do you know about this point right here? X is what? 0. That's how you always find a y-intercept. So it might be a weird, funky decimal, but plug 0 into this equation in your calculator real quick. Plug 0 in for x. It's going to give you some weird, very weird decimal. That's okay. Don't be afraid to tell me what it is, because it's probably right. 1.90. I believe that. I believe that. So yeah, since E is a weird number, if you plug in normal numbers, you'll still get a weird number. So you have a lot of weird numbers floating around sometimes because E is weird itself. But that's fine. There's a y-intercept there. I don't think there's anything else to say. I mean, we could harp on the domain, right? Negative infinity to infinity. Range is negative infinity up to 2, right? And behavior, limit as I go to negative infinity goes to 2. Limit as x goes to positive infinity goes down to negative infinity. We can do all that kind of crap. But that's a good rough sketch. Great. So same thing we've been doing. Any questions over the graph stuff? Same things. Same things as always. Great. Well, let's see what else they could possibly do. They are going to call back to an old skill that we probably need to refresh on. Average rate of change. Now, we sucked at this a long time ago, so I'll probably have to give you a complete review of it. Let's talk about average rate of change real quick. Average rate of change. Call back to way back in like unit 1 or something like that. Average rate of change is a fancy word for slope. Slope between 2 points. If they give you any 2 points to find the average rate of change between, and that's what all these are on the board right there. They're intervals and things like that. See, part A says -4 to -1, right? That's an interval. B says 0 to 3. But if you have something from one number to another number, well, whatever this function is, I don't know what it is. But when you plug in A, you're going to get out f of A. And when you plug in B, you're going to get out f of B. And since this just means slope, slope is just rise over run, correct? So the rise is whatever this y value minus that y value is. And that's just f of B minus f of A. And that's over the run, which is this x value minus this x value, which is B minus A. So there's your equation for average rate of change. It's the difference in the y's divided by the difference in the x's because it's slope right there, okay? Now, don't think that's too complicated. Let's see how you would actually apply this to these particular problems. So let's do part A. Part A says, for this function that we already graphed a minute ago, what's the average rate of change on the interval -4 to -1? That was roughly our graph, correct? What they mean by this is if you found a point at -4, there's a point at -4, would you agree? And then you went all the way over to -1. There's a point on the graph, right? All they're asking for when they ask for average rate of change is the slope between those lines. So what's the slope of that blue thing right there? That's the main thing. Last time I found it very helpful for you guys to not write it like this, just to say, well, can you just find me some x and y coordinates and just do rise over run like normal? So can you plug -4 into your equation? Take a minute. Plug -4 into that equation, and we'll just see what the y value is. Equation again, -2e to the x minus 3 plus 2. That's what g was. Yeah, -4 into that. Yeah, into that. Yeah, which is really weird. 1.99. Give me as many decimals as you got. All right, sounds good. So when you plug in -4, you got out that thing, fair? Repeat. Plug in the other one, -1. Plug -1 into that equation, and we'll see what y value we get out there. Great. Thank you very much. All right, so to keep it simple, what are we trying to do? Find slope, right? Well, forget all this heavy theory. If you don't want to use the equation, you don't have to. But you do need to know what the concept is. I need to find the slope between these 2 points. So we can just do rise over run. Let's see. It starts up here, and then it goes down just a little bit. Would you agree? So the rise is negative, went down. How much? Well, this one minus that one, right? So take your 2 answers. Take all these decimal points minus all those decimal points, and we'll see how much it went down by. .0340 was after that? 80. Okay, probably about good enough right there. I like that. What's the run? You can just spot it. If that's how much it went down the y's, how much did it go over in the x's? 3. Well, there's rise over run. So you just divide this by 3 and you see what you get. I can't do it from there. 0.025. There you go. There's the average rate of change, the average slope between those 2 points. Not very much, is it? It's very, very tiny. Which is because this between these 2 points is pretty flat. Would you agree? The slope's almost 0 right there, but it's going down just a little bit. So we got that right there. Let's practice it again. Same idea. We'll use the exact same function. The -2e the x minus 3 plus 2 function. Same graph. We'll do the same analysis. Part B, they're asking you for the average rate of change on the interval 0 to 3. So this time, the 2 points are going to be the one at 0. Didn't we find that already in the last problem? What was it, 0? That was the y-intercept, wasn't it? What did we get for that? I forgot. What was the y-intercept on this? Or we can just plug 0 in again if we want. Now we'll just do it again. Plug 0 into this thing. Let's see what we get. What was it? 1.90. Give me a few more. Okay, let's just do it again from scratch. Especially when I find slopes, I would have a lot of precision because the changes might be very small, so I'll make sure I have lots of decimals so I don't jack it up. Plug it in 0. Plug it in 0. 1.90 something. 5863. Sounds good. All right, that's lots of precision. We can't do any better than that. Well, there's where it is at 0. I know where it is at 3 just by looking at the equation. What's 3 minus 3? You should know what anything to the 0 power is. No, it's 1. And 1 times -2 is -2. And -2 plus 2 is 0. So right there at 0 is going to be. So if they ask you for the average rate of change on this interval, again, just rise over run. Don't make it too complicated. I can fancy it up with a whole bunch of theory and stuff like that, but just rise over run. Don't you agree it went down by this much? Yeah, okay, so it went down by 1.900425863. Great. How much did it run over by? Well, this was at 0 and this was at 3, so obviously 3. And your answer is going to be whatever that is divided by 3. Sweet. So you got yourself a negative slope there. Makes sense again between these 2 points. This thing is, in fact, going down. It looks to be going down steeper than last time, right? More of a negative slope. And yes, it is definitely more negative than it was before. So they're just throwing that in here. I don't know why, honestly, they're throwing this in this section, but they are. So it's a callback to things before. Average rate of change. That's good to know. That's about it. All right, let's just practice one more money one or so. Make sure we got everything down where you're okay. Let's see if you can do this one all on your own. You don't need me. Well, Chandra deposited $1,500 in a savings account. Pays 2.5% annual interest. Compounded continuously. That's the buzzword. Which equation do you use when it's compounded continuously? The one you just wrote down. So see if you can find where the numbers go, plug them into that equation. Again, if you don't know how to turn a percent into a decimal, just divide it by 100. $1,500 is the principal they invested. Time she's doing this for is 4 years, so T is 4. Just make sure you know where your E button is and you're fine. Setup should look like this, right? Cool. Did you plug it in your calculator? What'd you get? All right. I'll believe you all said in unison, so it sounds pretty promising. Cool. Have we got any problems typing things in? Nothing like that? We're good? All right. That's pretty much it then. I don't think there's anything else huge to worry about. The only other last ditch effort is if you can't solve something by hand, what can you always turn to as a cop-out? Solving by graphing, right? So if you ever need to do that, you could. I'd strongly encourage you not to do that unless you absolutely have to. For example, this problem right here, the only trick you have right now is to get the bases to be the same, right? This doesn't even have a base, does it? I mean, it's 5. But is there any way to write 5 and this base of 2.71 to be the same? Not really, is there? So what you could always do is what? Move things to one side, right? Set equal to 0, see where it crosses. They don't even say I do that. They say do something weird, but you can always just do my method. It's fine. And so if you get in a jam, you can always solve by graphing. Decimals are okay this time for a lot of these because you get some weird things out, but that's about it. So there's section 7.3. Due on Friday. Total work day tomorrow. We'll warm up tomorrow and review this stuff, but that's about it. And don't forget to turn in homework 7.2.